Hello everyone, I am Dr. Belmont and today we're going to continue with the series of videos for the General Chemistry 1 course. I want to thank the recommendation of one of my students. I want to say hi. The recommendation of changing the app I think is going to be very useful for everyone. So let's go clear all and start the discussion that we're going to do today. So what we're going to discuss today is something that we call partial pressures. That means that in a system of gases you can have partialities in the ways in which you're going to describe it. So for example, imagine that you have two different boxes, right? And in one box you're going to have gas A and gas B. Gas A is going to be represented only by dots, right? And gas B is only going to be represented by what? By crosses. And since they are gases, right, they are very happy where they are. They like to fill up all the space that their boxes have. But since they are gases, right, that means that they can be mixed easily, right? I can do and perform in the same volume in which they are contained, right? If I remain volume the same, I can perform a mixture of the gases. I can put A plus B, and what I will have is, well, a lot of dots coexisting with what? With a lot of crosses, and they're going to be very happy, right? There is no problem without that. So if this is true, right, remember that since they are gases, they have pressures, and that means that there's going to be a pressure associated to what? To A, and there's also going to be a pressure associated to whom? To B. And if that is true, that means also that I am going to add what? The pressure of A times the pressure of B once I have added them. Very well, if this is true, and no matter what, when I add PA and PB, I know the addition of these pressures is always going to be higher than whom? Than PA. In the same sense, if I perform the addition of PA plus PB, this is going to be higher than whom? Than PB. So just by acknowledging this, I know that when I add PA and PB into a system, what I am actually describing is the total pressure of the system. Okay, so pretty simple. Let's move on and say that very well. So these pressures are modeled by gases. So what about if I bring here the ideal gas model? Right, and I model the pressure of A. Well, if this is true, simple, I'm only going to require what? The number of moles of A times RT over B. And in the same case, I can model PB, the same as what? As the number of B, RT over B. Very well. Now, let's remember that PT, total pressure, is going to be what? PA plus PB. So probably what it would be convenient is to make a substitution for the ideal gas model and see what we will get. Well, very well. So following that, the total pressure is going to be the same as what? As the number of moles of A times RT over B plus NB times RT over B. And look at this, we have a common factor, right? We have RT and RT as a common factor. So something that it could be convenient to do is to now model what? PT as the same as what? As the number of moles of A plus, oh my god, Na plus NB times RT over B. Very well. So if in our system we only have moles of A and B, then that means that PT, right, is going to be NT times RT over B, where NT is the same as what? As NA plus NB. Very well. That means that we can expand this model to what? to any sort of gases and moles of gases specifically that we need. So for example, if you have more than one gas, it would be simple. You would only have to add the P of A, the P of B, and the P of C, or basically anyone that you want. And this is very useful if you want to describe everything as what? As a total, right? But what about if you want to describe everything as a partiality? How do you think we're going to do that? Well, that's the main topic, so let's go and jump into that. So if I'm going to describe the system partially, that means that I'm going to describe what? One of the gases. For example, let's say that I want to describe PA. But remember that this is as a function of what? Of PT. So what I am going to say, right, is how much of A is inside of all the pressure. And we already know the descriptions for each of these pressures, right? It's going to be very simple. So for A, it's going to be only an A times RT over B. And all of this is going to be inside of what? Of NA plus NB times RT over B. And guess what? These ones cancel. So the partiality of A inside of the total of the system is only going to be a function of what? Of the number of moles, which is pretty cool, right? So I only need the number of moles of A and the total number of moles in the system, which is in this case is the number of moles of A and B. And this is going to be called a new name. This is going to be the fractional number for A. So clearing this equation a little bit, what I say is that PA over PT is going to be the same as the fraction mole of A. Very well. So let's continue and clear this equation a little bit more. What I will get is that PA, right? Let me rewrite this. It's horrible. No, red. I like red. So let's say that I have PA. And this is going to be, sorry, I'm still learning how to use it. PA over PT. And this is going to be XA. Awesome. So clearing this equation, what I will get is that PA is the same as what? As XA times PT. And I can mimic this for basically every single other member of the system. So for example, if I have PB, this is going to be what? X of B times PT. And any sort of equations that I want to model would basically follow the same model. So if I have, for example, PT, and I know that this is PA plus PB, right? I can also describe PT as what? As the fraction corresponds to A times PT, right? Plus the fraction of B times PT. Very well. So how are we going to use this in a more practical system? Oh, believe me, it's very easy and it is very useful. So let's take, for example, that you have a box. Here is the box, okay? And in the box, you're going to have different gases. For example, neon, for example, argon, and for example, xenon, right? And they are going to occupy all the space of the system. And they are asking me to describe the pressure, only the pressure, the contribution of the pressure that the neon is giving, right? Well, first of all, I need to have some information. And they are telling me that the total pressure of the system is 2.0 atmospheres. It is easy, right? I just connect the system, right, of measurement right here to measure the pressure, right? Something like this, for example, you see. And they have like a needle here to measure pressure. There you go. And I measure that I have 2 atmospheres. And they also tell me that I have the number of moles for each gases. For example, for neon, I know that I have 4.46 moles, right? Now for argon, I'm going to have 0.74, moles, and for xenon, for xenon, what I am going to get is 2.15. So those are the numbers that the problem gives me, right? How are we going to solve it? Well, let's go and summon what we already know. And I know that PA is the same as what? As XA times PT. So let's change A for something that we need. For example, P of neon, right, is going to be the same as what? Of X of neon times what? 2 atmospheres, because that is the total pressure of the system. What are we only missing? Well, X of neon, and X of neon is pretty simple to obtain. So if this is true, XE is going to be what? 4.46 moles over what? 4.46 plus 0.74 plus 2.15, and all of these are moles. So moles with moles will go away, and it's perfect, right? Because it is what? The fraction mole of neon, and fractions do not have units, they are also numbers. And when you perform the math, what you're going to get is 0.607. So the partial pressure of neon is going to be the same as what? As 0.607 times 2 what? Atmospheres. And it makes sense, right? Because at the end, what I am looking for, pressure of neon, and pressure has to be measured in atmospheres. So I'm going to let you go and do the math. Please let me know how this goes, right? And it was a pleasure to be with you again.